Hello, everybody. My name is Dr. Antonis Papadakis, and today I will be presenting KYAMOS Limited work on a project funded by the Research and Innovation Foundation under the title Real Life Simulation of Green Software in the Cloud. The code name is codevelop /GT03220081, and this project was funded in the frame of the Recovery and Resilience Plan Cyprus Tomorrow, Next Generation EU, through the Cyprus Research and Innovation Foundation. It was conducted in collaboration with Frederick University and the University of Warwick, and it will be presented by the project coordinator, myself, Dr. Antonis Papadakis, CEO and founder of KYAMOS Limited. In the project, it was meant to develop an ICT software that will include in total 6 simulation modules. The first one in WP3 was the radio frequency filters. The second one in WP4 was the electromagnetics module. In WP5 it was the semiconductor. In WP6 it was the wind turbines. In WP7 a battery module, and in WP8 a thermal module. Starting from the WP3, the radio frequency filter, we have utilized the modified telegrapher equations for the voltage and the current, as you can see. In order to model RF filters, we utilized the finite difference time domain in one dimension and calculated the S parameters. And we applied this software on non-reciprocal bandpass filters for communication systems. We utilized the user-friendly graphical user interface for easy schematic circuit design, and we added components such as wires, resistors, parallel series SC resonators, inverters, etc. And we validated our results through software and also through the literature. Here you can see on the left a friendly GUI with drag and drop capability, so you can design your module. And the solver is automatically designed in Python to be run and also display the results. And you can see, for example, S parameters such as magnitude and phase, 1, 1, and 1, 2 on the right. Moving into electromagnetics, we have developed solvers for Helmholtz equation in finite elements in 3D, Maxwell equation solutions using lattice Boltzmann, PGK, for scattering electric and magnetic fields, and we utilize the Poisson equation solver in lattice Boltzmann using D3Q19, which was done for the first time to our knowledge, and also in finite element using CUDA-aware MPI. We have tested our finite element Poisson solver against a well-known commercial software, which is also parallel, and we were found to be 60 times faster on very slow Tesla K80 cards. So using our new Tesla V100 cards, we could go up to 100 times and even more. And of course, by buying new cards like the H100, and we can move even faster. Now, the numerical methods used was the lattice Boltzmann D3Q19 MRT for the, and also OBGK and finite element. We also created our own conjugate gradient method, which also supported complex numbers, and we applied it in electromagnetic field scattering and refraction to and from the media. Here are some just of the results. On the left, we can see the finite element conjugate gradient solver creating an analytical solution of a voltage of 0 and 100 applied on the cathode and anode, and you can see we get a linear distribution. And on the right hand side, we can show that in the GUI we have a box which we used in the simulation, and we utilized NetGen meshing software, incorporated it so that we can generate the finite element mesh that was used for the simulations. On the left here, we see the Helmholtz solver. We apply a point source in the middle, and we apply absorbing boundary conditions around the domain. And you can see the results being produced as expected. On the right hand side, we show a benchmark test case in 3D, lattice Boltzmann, which is validated exactly with the results. Now moving to WP5, the semiconductors, we have basically developed a solver which solves the Poisson equation that includes electrons and holes charges as well as donor and acceptor levels. It is also coupled with the Drift diffusion equations for electrons and holes. And within the source stem, Se and Sh, of course, we apply shockley reed hole recombination and other ionization processes. This solver is basically developed using all lattice Boltzmann in D3Q19, but we used BGK for Poisson equation and MRT for the Drift diffusion. Basically, the velocity comes from constitutive relations of depending on mobility and electric field. So their input, VE and VH, are input to the Drift diffusion equations through the Poisson voltage and electric field. And we applied it in a silicon PN junction for demonstration purposes in 3 dimensions. We validated, of course, the solver in 3D. And then also we applied electron and hole and also forcing terms and combined them together in order to solve the silicon PN junction. Here you can see on the left the electric field as it was developing when basically the 2 PN junction tries to settle before we apply any biasing. And on the right hand side, we can see the carrier density that is being developed by the lattice Boltzmann MRT for the Drift diffusion for the electrons and the holes. Moving into another module, the wind turbines, we developed a solver which basically holds the incompressible Navier-Stokes, and on top of it, the theory of dynamic load coefficient and power calculation for the blade. Here, what we do, we basically develop a model that, given a certain airfoil, you can design the nacelle, the pole, and the 3 blades, custom made. Then you can develop your wind turbine in open cascade, export it in STL, and automatically load it into our software. All the user has to do is to define whether they are rotatable or whether they are stationary. And the software calculates with STL, finds the intersecting points, applies an innovative second order boundary condition, no slip on these structures, moving and non-moving, and rotates basically the parts at every time step, recognizing transitioning of fluid to solid nodes and solid to fluid nodes, and also identifying the cross edges between that cross the STL elements automatically, and calculate forces, moment of inertia, center of gravity, center of origin, torque as well, and rotates the whole structures or keeps them stationary if they are stationary. So a passing wind. We have also have the ability to place multiple wind turbines. And we've been able also to provide streamline visualization in Open Cascade on top of PL plot. And we can accurately validate our results. As you can see, moving into the batteries module, we basically solve 4 equations, which are diffusion equations, and then the battery warmer for electrochemical kinetics, and the exchange current density equation for the ions, and also in the separator, in the electrodes and the electrolyte. The numerical methods used are all lattice Boltzmann, BGK, D3Q19, and we cover basically lithium concentration and potential, and it is applied in lithium-ion batteries. On top of it, we developed a user-friendly GUI for the lithium-ion battery design, as you can see on the left, and we also embedded in-house bicontinuous complex porous structure generation software. So our clients can generate porous structures with the desired porosity. And here on the left, we can visualize the battery microstructure. And on the right-hand side, we see a cross-section visualization for lithium transport characteristics, validating our results on the anode and the calculation at the cathode. And finally, in WPA, in thermal, we have developed 2 solvers, all in lattice Boltzmann. The heat diffusion solver, which is a time-dependent diffusion solver with a source cell, And secondly, an attraction diffusion equation solver, the so-called conjugate heat transfer solver. All in, that is was one D3Q19 MRT regarding the attraction diffusion equation, and D3Q7 the heat equation. The heat equation was applied to heat transfer in solids, whereas the attraction diffusion equation, or conjugate heat transfer, was applied in solid fluid interactions. On top of that, we have developed a convolutional neural network model predicting internal temperature given the surface temperature distribution. This AI prediction can allow our customers, for example, to predict the internal thermal distribution given the external thermal maps, for example, from thermal cameras on certain elements. We also developed a user-friendly GUI for applying boundary initial conditions, an option for domain states to choose from solid to fluid or fluid to solid. And we supply high resolution and low computational times. And here we can see two heat maps developed by PLplot in our software. Thank you very much. I would like to say special thanks to the Research and Innovation Foundation for the funding and support, and also to our partners in this project, Frederick University and University of Warwick, and most importantly to KYAMOS members that have worked hard in order to make this project possible and successful.